Welcome to this channel. Today we are discussing chromatography and solid phase extraction. We are just going to deal with some part of liquid chromatography, not entirely, because we will be having another discussion. So some of the terminology and separation modes. So we have adsorption chromatography, where the stationary phase is an adsorbent, for example silica gel or any other silica based packing. The separation is based on repeated adsorption desorption steps. Then we have normal phase chromatography, where the stationary bed is strongly polar in nature and the mobile phase is non-polar. So polar samples are retained. On the polar surface of the column, packing longer than less polar materials. So reverse phase chromatography, the stationary bed is non-polar in nature. So the mobile phase is a polar liquid, such as mixtures of water and methanol or acetonitrile. So the method, the more non-polar the material is, the longer it will be retained. Some of the branches of liquid chromatography family, we have adsorption, partition, gel permeation, gel filtration, and so on and so forth. So you can be able to see and majorly the mode of separation, and then so you can be able to see how such interactions occur. If you look at this reverse phase, where we have polar mobile phase, and then we have non-polar stationary phase. Then we have ionic pair, bipolar mobile phase, non-polar stationary phase. Then we have this situation here also, where we have now this case polar stationary phase, non-polar mobile phase, that is of course normal phase. Then we have ion exchange, where we have now ionic stationary phase and mobile phase. Then we have size exclusion. Also here we have porous stationary phase. That's what we call ion exclusion. So higher performance liquid chromatography utilizes a high pressure liquid mobile phase to separate the components of a mixture. These analytes are first dissolved in solvent and then forced to flow through a packed small particle chromatographic column, where the mixture is resolved into its components. Higher performance, high pressure, and high performance. That is the meaning of high HP. Then the solution depends upon the extent of interaction between the solute components and the stationary phase. The difference between high performance liquid chromatography and classical liquid chromatography. So we have what we call reusable stainless steel columns, and you will see them later, those columns which are reusable. Then column packing with very small particles and the continual development of new substances to be used as stationary phases. Then relatively high inlet pressure and control flow of mobile phase. Then there is precise sample introduction without the need for large samples. Then special continuous flow detectors capable of handling small flow rates and detecting very small amounts. Then you also have automated standardized instruments. It is also having a rapid analysis and high resolution. So that's why most of the liquid chromatography nowadays are referred to as high performance liquid chromatography. We hardly use classical liquid chromatography. Then we have advantages and disadvantages of liquid chromatography. The advantage is that it is having good speed, high resolution. It is very sensitive. The results are reproducible. Then it's accurate and it can be automated. Then disadvantages is cost. Remember the mobile phase, the solvents, and many other things that even the machines not very cheap. The complexity, because you have to know how to vary the mixture ratios of the solvents, and you need to really know how to choose the column. Then low sensitivity for some compounds, irreversibility of adsorbed compounds not detected, and then co-elution difficult to detect. So more on reverse phase liquid chromatography. So of all the different modes of separation, reverse phase chromatography is very common. So you can see it's the most widely used mode of HPLC. 70%, 75%. It separates molecules in solution on basis of their hydrophobicity, non-polar stationary phase, and then polar mobile phase. Very important. Then in practice, non-polar functional groups bonded to silica. So we have stationary phase. Our stationary phase functional group bonded to silica. Then this corresponds to a volume. Then alkyl groups like the C4, C8 and C18. The rotation increases exceptionally with the chain length. So mobile phases, polar solvent with addition of less polar solvent like acetonitrile or methanol. So you can see then the packed column and the stationary phase. So as you can be able to see here, some of the columns that we were talking about. So packed liquid chromatography columns usually made of stainless steel and carefully filled with material, and the heat of these are the heart of liquid chromatography, the packing and the column. This is where separation takes place. So the stationary phase fills the column. Its properties are critical to the separation. So some of the molecular interactions. So majorly covalent, hold molecules together, a bit orbital overlap. We have ionic interaction, electrostatic attractions. Then we have polar, hydrogen bonding, dipole. Then we have pi stacking, vary from electrostatic type interactions. Then we have non-polar, the van der Waals, weak induced dipole. So retention mechanisms in liquid chromatography. Liquid chromatography is a dynamic partition adsorption process. Analyte molecules while moving through the porous packing bead bead tend to interact with the surface adsorption sites. Depending on the liquid chromatography mode, different types of the adsorption forces may be involved in the retention process. Like we said before, some of the non-polar interactions, van der Waals, and so on and so forth. So hydrophobic interactions are the main ones in reverse phase separations. Remember here the stationary phase is non-polar. So dipole interactions are dominant in normal phase mode. Remember, normal phase, the stationary phase is polar. Then ionic interactions are responsible for the retention in ion exchange, if you remember. Then retention in liquid chromatography is competitive. Analyte molecules compete with the eluent molecules for the adsorption site. So the stronger analyte molecules interact with the surface, and the weaker the eluent interaction, the longer analyte will be retained on the surface. So elution order in liquid chromatography. So remember the elution order in normal phase versus reverse phase. So generally you will realize that when you are dealing with the normal phase chromatography, remember when you say normal, then stationary phase is polar. So it means that low polarity mobile phase, so low polarity mobile phase, and you can be able to see. Then medium polarity mobile phase. So it means that if you are dealing with the normal phase chromatography, then you are mobile phase should have very low polarity, and that will give you a very good separation. Compared to this is not very good separation. Then the same with reverse phase. Now when you're having reverse phase, remember stationary phase is non-polar, so it means that your mobile phase need to be having high polarity, so that you have a good separation. Otherwise, if it is having low polarity, then you are going to have poor separation. Then physical properties of stationary phase particles. So in HPLC, separations are based on the surface interactions and depends on the types of the adsorption sites. So modern HPLC adsorbents are the small rigid porous particles with high surface area. So key parameters: particle size is 3 to 10 micrometers. Particle size distribution as narrow as possible, usually within 10% of the mean. So it means that they should not be having different sizes. That will really affect separation. So pore size very small, 70 to 300 angstroms. Then surface area 50 to 250 meter per square gram. So that tells you the surface area is very large. And then bonding phase density, number of adsorption site per surface. You can see that 1 to 5 per 1 nanometer. So you can see that there is a lot of what we call number of adsorption sites. So it's very efficient. Then the most popular particle is silica, different morphology for different applications. So you can be able to see here. So free silanol, then adsorbed water, geminal silanol, dehydrated oxide siloxane bound and reactive silanols. So chemical modification to silica can be happen residual silanols or functionalized groups. So that one to achieve different separations. So silica by itself cannot do the job needed by modern liquid chromatography users. It must be functionalized and modified to suit analytical problem. That's what we are hearing about C4, you are hearing about C8, and you are hearing about C18. You can see that this is a C8. Yeah, so that is how we are modifying it. So that is generally that silica that is used as certain stationary phase. So chemical modification to silica, you can be able to see what is happening there. So this is like a C18 or something. So that is how it's done. So groups are usually attached via reaction of an organosilane, which can be pre-polymerized in solution. Besides attaching groups, it is also possible to polymerize the silica. Purpose stability and low pH, more coverage. Then monomeric phases are more reproducible, easier reactions to control. Then end capping fully reacts the silica surface, remove silanols and their acidity, more coverage. So common liquid chromatography stationary phases, we have silica, which this is majorly for non-polar, normal phase. It is for separating polar or non-ionic organics. Then propyl, this one is for reverse phase, for hydrophobic interactions. Then we have C8 for reverse phase. Then we have C18 also for reverse phase, non-polar solute strongly. Then we have the cyano, reverse phase and non, and normal phase, more polar than C18, unique selectivity. Then amino, reverse phase, normal phase, and weak ion exchange. Reverse phase used to separate carbohydrates. So it means that you really need to know the packing material before you do your separation. So continuing, the phenyl, that is also for reverse phase, retain aromatic molecules. Then we have diols, both reverse phase and normal phase utility. Then we have nitro, normal phase, separate aromatic and alkene containing molecules. So polar stationary phase interactions. So these are just generally the interactions that happen. It's like this one is dipole, then amine, hydrogen bonded, then diols, hydrogen bonding. So you can see the interactions. Then ionic stationary phase interactions, where we have electrostatic. You can see this particular group here interacting with a sulfite on this particular stationary phase. You can see mostly ionic is electrostatic interactions. Then non-polar interactions, we have the van der Waals. Then we majorly the van der Waals. Van der Waals is what predominates non-polar stationary phase interactions. You can be able to see. Then a good choice of stationary phase depends on the analyte. Very important, we've talked about it before. So if your analyte is of this nature, this is hydrophobic, so you'll choose mechanism is non-polar. So if we have this, of course, hydrogen bonding, we'll choose mechanism is polar. If we have this, then it is ionic, mechanism is ion exchange. Then in mobile phases in liquid chromatography, the type and composition of the mobile phase is one of the variables influencing liquid chromatography separations. So desirable properties, one is purity, two is detector compatibility, we have solubility of the sample, low viscosity, chemical inertness, and reasonable price. So mobile phase differ for each liquid chromatography mode. So normal phase solvents are mainly non-polar, and reverse phase eluents are usually a mixture of water with some polar organic solvents such as acetonitriles. For size exclusion, liquid chromatography has special requirements for mobile phases. It must dissolve the polymers, must also suppress all possible interactions of the sample molecules with the surface of the packing material. So very important, very important. Then the control of eluent polarity, isocratic elution, the eluent composition remains constant as it is pumped through the column during the whole analysis, but gradient, the eluent composition is steadily changed during the run. So that would also, it will require some knowledge. So you can see this isocratic, and then you can see the gradient. Then the instrumentation, very simple. We have pumps, mixtures, and ejectors going into the column, and then separation happens in the column, and then it reaches, molecules reaches the detector, and then they are displayed in the computer. Very important. So where there is a lot of complexity is this particular first point, because here is where you have to do and good pressure, you have to vary the mixtures and amount to be injected, and of course the solvents and everything. So this is generally a sample of liquid chromatography instrument. So you can be able to see solvent reservoirs, we have solvent degasser, pump, we have autosampler, column oven, and a detector, that is DAD. We will look at it. So detector is the lowest here, I mean the one on the base, then we send it to the computer. Very simple. So we can be able to see purpose of key liquid chromatography components. Column, very important, separation chemistry, tubing to detector flow cell, then it goes to detector, signal transduction, amplification, scaling, and filtering, so analog output. Then we have data acquisition, digitalization, digital output. Then we have a chromatogram generally. Then the liquid chromatography pumps, modern pumps have the following parameters. They have to have a flow rate range of 0.01 to 10 milliliter per minute. Then pressure range from 1 to 5,000 psi. Pressure pulsation less than 1%. Then types of pumps: constant pressure pumps and constant flow pumps. So reciprocating piston pumps, small internal volume pulse flow. Then syringe type pumps, limited solvent capacity. Then pneumatic pumps. So those are some of the pumps we have. Then we have temperature control in liquid chromatography. So as you can be able to see, thermoelectric heating and cooling, the ability of the surface to produce or absorb heat when current is applied across the junction of two dissimilar conductors or semiconductors. So the effect can be reversed. For example, heating turned to cooling by reversing the DC current through the junction. So also known as the Peltier effect, after its 1834 discoverer, a French watchmaker. So one of the Peltier device couple consists of one N-type and one P-type semiconductor itself. So you can be able to see now overview of liquid chromatography detectors. The common one, refractive index. We have UVVs, and then we have fluorescence detector. So less common ones are the conductivity, mass spectrometric, and evaporative light scattering. Desirable features of a liquid chromatography detector: one, it has to have low drift and noise level, high sensitivity, fast response, wide linear dynamic range, low dead volume, cell design that eliminates remixing of separated bands, insensitivity to changes in types of solvent, flow rate, temperature, operational simplicity and reliability, and non-destructive. It has to be non-destructive. So baseline noise and drift, you can be able to see. So detector response, the definition of detector response depends on the whether it is mass sensitive or concentration sensitive. So mass sensitive, you can be able to see. Then concentration sensitive, you can also be able to see. So some of the detectors you can see, a chemical compound could interact with the UV light. A beam of the electromagnetic radiation passed through the detector flow cell will experience some change in its sensitivity to this interaction. So you can see all that. So flow cell design, this is just the design of flow cell. Things to note: parallel light beam, flow cell volume, and optimization of cell geometry. So you can be able to see all that in the mercury vapor lamp emit very intensive light by filtering out all other emitted wavelengths. manufacturers have been able to utilize this 250 4 nanometers line to provide stable, high sensitive detectors capable of measuring sub-nanogram quantities of any compound which contain aromatic ring. The 254 nanometer was chosen since the most intense line of mercury lamp is 254 nanometers, and most of UV absorbing compounds have some absorbance at 254 nanometers. So diode array detectors can acquire all UV visible wavelengths at once. So advantage is it is sensitive, it has good speed, and disadvantage is resolution. So other detectors, we have fluorescence detector, we have electrochemical detector, and evaporative light scattering. So putting it all together, liquid chromatography method. So its importance: without a good method, coelution can be missed, unable to detect as a key components. So basic consequences of method changes. So you can be able to see. Choosing an LC approach, you have to check resolution, that is should be greater than 1 to 1.5. Short separation time 5 to 30 minutes. Good quantitative precision or accuracy. Acceptable back pressure. Narrow peaks. Minimal solvent use. So overall strategy: first, select an appropriate method. If liquid chromatography is best, then determine nature of sample. Exploratory reverse phase runs, i.e. first simple gradient with C18 phases, are usually helpful in assessing retention and polarity. So those ones you need to check. Then solid phase extraction. What is solid phase extraction? The separation of an analyte or analytes from a mixture of compounds by selective partitioning of the compounds. So between a solid phase and a liquid phase. Comparison between conventional liquid extraction and so solid phase extraction, selective towards functional groups. Liquid extraction, selective towards solubility. Solid phase extraction, more choices because no miscibility, which is better. Liquid extraction must avoid miscible solvents. So solid phase extraction, concentrate analytes, which is better. Liquid extraction can concentrate analyte after stripping. So this is how separation occurs. Column conditioning, solvate the solvent, then equilibration removes excess conditioning, solvent matches with the analytical conditions. So you can be able to see column conditioning, then column equilibration, then sample application, then interference elution, you can be able to see, and then analyte elution. Solid phase extraction, so conditioning the cartridge, you see this is non-conditioned, this is now conditioned. So solid phase extraction cartridges have a range of chemistries that are often similar to those of liquid chromatography stationary phases but are optimized for adsorption, desorption. So you can be able to see automated solid phase extraction system for sample cleanup, the spark symbiosis. Can be able to see, can be hyphenated with liquid chromatography, mass spectrometry, non-nuclear magnetic resonance, or used as a standalone sample pretreatment. So we can do further reading, Scooch, Holler, and Crotch, chapter 28, and many others. We want to thank you for listening and keep supporting. Thank you.